I mean, for rest of all of you, hello. So what I plan to do is, like, this is the third edition of the school which is happening, and the main motivation is that in the main school we will cover topics like graph neural network, transformers, some generative model, all this fancy stuff. But the baseline sort of tools which we require to go for those advanced concepts are basic Pytorch stuff, like basic machine learning. So, this is a school on machine learning, and you have already learned some concepts in NumPy, Python, etc. However, like today, I will introduce you with basic notations of Pytorch, the default machine learning library which we will use for all the graph neural networks and stuff like that. Okay, I mean, some part I will share with Rajdeep, and we sort of discussed that Pytorch is the base library on which we will do all the codings. So if you haven't come across Pytorch before, it's absolutely fine. That was never a prerequisite. But I will assume that you just know how to use NumPy. By the way, at any point, since I'm sort of sharing my notebook, I'm not looking at you directly. Okay, so at any point, if you have questions, just unmute yourself and raise your voice. I will be happy to be interrupted. No issues. So most of the materials, like you can take it from the Pytorch website. There are amazing tutorials there, as well as there are corresponding sort of courses on GitHub from Pytorch itself. Also on YouTube. You can look into them. Also, I personally prefer this University of Amsterdam course, which is UVA Deep Learning, one of my personal favorites. So I sort of taken quite some material from there as well. So you're highly encouraged to look into these sources. As well as when we first handed out the sort of curriculum for the courses, there were n number of resources which were listed there. So you're welcome to look at those as well. So let's sort of try to let's go through it. So first thing first, we will first try to introduce Pytorch tensors, which are just the analogous stuff for NumPy ND arrays, and just try to see whatever you know in terms of operations on NumPy ND arrays, how do we repeat the same things in terms of Pytorch tensors? Okay, so let's do it. Can you just confirm that this thing is scrolling, like when I scroll my notebook on my desktop, it's scrolling in the video?
Yes, sir.
Yeah, very good. So you can see if you have, it will be also great if you just download the code from GitHub, where the link you already have with you, the mail I sent out last night, and you can try interactively. The whole point is that we want to learn it hands-on. Okay, so as we are moving along, you can also give it a try. So you can see that we have a bunch of things imported. So the first thing is that you should have NumPy, Matplotlib. However, if you just install Pytorch, this will come with Pytorch. But we have also used a plotting library called Seaborn. Okay, so you have to probably do a pip install Seaborn, and also you have to do a pip install TQDM. TQDM is a very handy tool which actually shows how things are progressing. So I will sort of encourage you to do that. Now, once you do it, it's good to sort of know where you are in terms of your working directory. So just print, like import OS and os.sys.path. So you can see in the path variable, it's a sort of a list. It's a list of strings, and it gives what are the environments which are handy, like available in my working environment. So if you have installed a library which you want to use but don't see here in the list of os.sys.path, maybe you have to manually append that in this list in order to bring that environment inside your Python working directory. So you can see that like my everything is under my Miniconda work environment. So all that stuff I have in my sort of working packages, okay, in the working environment. So keep a track of that. Now here it is, like very simple. You do an import torch, and you just print torch.version. The latest version is 2.7.0, and it prints it. Now it's good to know what is the hardware you're using for using the machine learning stuff. If you are using like an Ubuntu on an Intel machine, probably like the device you have to use is like CPU. The torch.cuda is like an inbuilt library which will automatically detect it. I'm doing it on like a Mac, so it detected MPS, and it has set the device to MPS. If you have GPU available, it will set it to CUDA. Okay, that's it. Also, for the now in our environment, we have two libraries which have random number engines. One is the Torch, and another is NumPy. So we really need to set a seed to the random number generator for both of them in order to set the random number generator state, so that we can like ask for reproducibility. So that's the thing. You just set the seed of the random number generator. Okay. Now comes the first concept. So until now it was all trivial. Anything problematic? Anyone found things are not working? Okay, I
Sir,
hope
can
it's
you just discuss the CUDA part?
so. CUDA part is like there is a hardware on which all these codes will run. It can be your default CPU of the computer where all the backend computation will happen. If you have a GPU hardware, graphical processing units, which makes the machine learning codes very fast, it's there. The modern Apple ones comes with this Apple Silicon hardware, which is called MPS. So it might be that a priori you're sitting on a random machine and you don't know what hardware is available to you, but you want to use the best available options. In that case, what do you do? What you do is the following. You use this snippet, you use this backend library called torch.cuda. Okay, so if torch.cuda is available, that means if the GPU hardware is available and your Pytorch can access that, then this if condition will turn to be true. So if that is the case, the device variable, which is just a string, will be set to CUDA. If this is not true, then if torch.backend.mps, which is to check whether the hardware is Apple Silicon, if that is found, then it will set to MPS. Otherwise, it will be assumed to be a default Intel machine, and the backend hardware will be set to CPU. So whatever it is, the code snippet will automatically detect that and set the device variable to that particular string. So since I am doing it on my laptop, it detected as MPS and set to MPS. However, depending on where you're working, you might find the output of this code snippet as CPU or CUDA, whatever. So if someone is running this part of code and has got some output here, they may tell what they have got. Okay. So if you are trying, you can give it a go.
CPU, sir.
Okay, so Bapi Boshak has like access to GPU. So he has got CUDA. Someone else said CPU. So according to what machine you have the corresponding device. Great. So now what I was discussing is the sort of the seed. Now, of course, in notebook these days and etc., if you just take your cursor to any of the functions which you think you don't know, it gives you like the description. So, and Visual Studio Code is also amazing. Like it's there in other stuff, PyCharm, etc. But in Visual, I prefer Visual Studio Code these days. So if you just don't know how things work, you can just take your like mouse cursor on top of that variable, and you can see that there will be a pop-up window which will give you a description of what those functions are. So you just don't need to separately open a browser, go for the manual and try. Like it's all there. Now comes a concept called torch tensor. So in Pytorch, the torch.tensor is the similar object as in NumPy ND array. So whatever is NumPy ND array, it does. Torch tensor almost exactly is like a twin brother. It's just given a different name. It's under the Pytorch library. So let's start understanding. Let's build our intuition. So what we are looking for, like all these operations are just some specific matrices of or tensors of different ranks. Okay, so here what we will do, we will make a small list, maybe one-dimensional or two-dimensional stuff, and then try to see how do we deal with torch tensor and what are their corresponding NumPy ND array, so that we can do a one-to-one comparison and build our intuitions. Okay, so let's do this. Here you see we have just a 2x2 list which is declared as data, and this is a list of a list which is like a 2D matrix. So if you just print it, it will be like 1 2 3 4 2x2 matrix, and you can wrap it with a torch.tensor data. So data was a list, you pass it through this function torch.tensor, and what it creates, it's a variable which is of type tensor. So remember, initially the data, this particular variable was a list, and this x data is a torch tensor. Now if we take the same data and pass through an NP array, so now this quantity NP array is a NumPy ND array. You can see here what pops up in the description, it's an ND array, whereas X data is a tensor. So ND array is the object inside NumPy and tensor is an object inside torch.tensor, but both of them are just similar things. It's a 2x2 matrix, but with different object type. Okay, good. So is there a way to convert NumPy ND arrays to torch tensors and vice versa? So let's try to do it. So you see that NP array, okay, was a NumPy ND array. You can see it from the description. When you pass it to the function which is inbuilt inside Pytorch library, which is called from NumPy. So from NumPy, what it does, it takes a NumPy array and converts it to a torch tensor. So what you pass is an ND array, and what you get is a tensor. That's how how simple it is. It's just a conversion. So if you print the type here, you get it as a torch.tensor. Okay, great. So the old data was NumPy, and also you can convert. So X data is sort of a tensor which was there, and if you wrap it with np.array, it becomes again a numpy.nd array. So both are convertible to each other, and there is like no deep mystery here. Great. So you sort of understood that from this very 0th level sort of example, that how ND arrays, numpy ND arrays, and torch tensors can be easily convertible to each other. Fine. So any questions until this point? I guess not. Great. So now let's go through some of the things you can do with torch like tensors. So these are all there in NumPy as well, but you can also do like create higher dimensional arrays or tensors with fixed number. So you can create torch.zeros, torch.ones, and pass a shape. So it will create higher rank tensors, all filled with zeros or all filled with ones, which are of same shape, which will have the corresponding shape. Also, like if you want to create a particular tensor with a given fixed shape, but all the elements are some random numbers drawn within the range 0 to 1, you use this variable torch.random. Okay, and there is an a range. So let's take an example. You want a 2 by 3 sort of matrix, but you want the elements of that matrices as random numbers. So like random, here you can see, no, actually not 0 to 1, like it's any random number. So here you see torch.random of the shape 2 by 3, and it gave you a tensor of shape 2 by 3 with random numbers as the elements. Also, you can sort of create any tensors of any shape where the elements are drawn from a normal distribution, standard normal distribution. So in that case, you just call this normal, okay? And you see the description says that the random number sampled from a Gaussian distribution with mean 0 and standard deviation 1. Great. So we can sort of play a little bit. So if we specify a shape, then we sort of define all these 3 variables, torch.ran, torch.ones, torch.zeros. It sort of create the tensors, so on and so forth. These are like random numbers. These are like all ones, all zeros. Okay. So now you have created tensors of arbitrary shapes. What do you want to do? You probably want to do some elementary operations with them, like addition, multiplication, division, so on and so forth. So before we go into start learning how to do additional multiplications, are there any questions? Clear until now? Okay, very good. Good. So first of all, you know from your elementary mathematics that 2 arbitrary higher rank objects can be added, subtracted, etc. if and only if they are of same shape. So here we have created 2 arbitrary matrices, both of shape 2, 3, which is torch.tensor 2, 3, x1 and x2. And you can see that you can just add them up and you get the numbers. Perfectly fine. Okay. Now, here comes the story of the devices. Look, by default, if you create something like this, a torch.tensor, then the tensor is created on the CPU device by default. So if you just print the device, it will return CPU. Now, you can put that tensor on your accelerating device for this case, we defined it like as MPS, someone will have GPU. So you better should do y dot to device. So this is a syntax which is like puts the tensor on us like the hardware you want. So you could have done like something like this. You can define torch dot tensor, and if you do like a double question mark, so let's, here you see in the description that the data you pass is anything. You could have passed the device here as well, but since we didn't pass the device in the argument while defining the tensor, it will be by default CPU. But if you let's say you write it something like this, something like there is a data 1, 2, 3, and then let's say we sort of put device equals to device. So, sorry, this is. So once you do that, let's say A, B, and then do like print A, B. Oops. Is it working? Yeah, so if you try this, you should see the device here. Just let me check if it's the environment is on or not. Yeah, and then to restart the module. Okay, never mind. So here you can see that the data I have like defined as a again 2x2 matrix, and I have done like some torch.tensor data, and then put torch.tensor. I have defined like data as device and have printed the device of the data. So in the first case, it came out to be CPU, and the second case, it came out to be MPS. So if you, those who are running on GPU, if you try to do this, the first one will turn out to be CPU, and the second one will turn out to be CUDA. Okay. So, and those who are doing on Intel machines, both will turn out to be CPU. So is this concept clear? Like how do you put like torch tensors on a particular device, accelerating device? Anyone has any question? I hope like I'm audible and stuff like that, right? Amir? Okay.
Yes, sir.
Okay, very good. Now, the algebra of all these tensors can be done in multiple ways. So before, like we have seen addition, and you add two tensors and store it to some other variables. Here you can see you have defined some tensors x1 and x2, random numbers. And if you do x2 dot add underscore, so this underscore is sort of, it adds the elements of x1 to x2, keeping x1 unchanged. So here you see that x1 was something, x2 was something, and it prints what is x1. It's like 0.95 blah blah blah, 0.80, x2 0.57, some numbers. Now once you do this x2 dot add x1, you see the x1 after the addition remains same, exactly same. However, the elements of x2 have changed. You can like visually compare and see x2 has changed. So what does this syntax do? This syntax adds the element of x1 to x2 without touching x1. Okay. Similarly, when you will find there can be many such stuff like dot add, similarly dot like multiply and stuff like that. So whatever tensor has been passed into the parentheses, that remains unchanged, and whatever it is added to, or like any algebraic operation it has been done to, that particular tensor changes. Fine. Good. So this is like it's called in place operation and things like that. So now we sort of introduce this concept called the view function. What it does, let's say we have an X which is a 4x4 matrix. Its shape is 4x4, it's printing. Now if we do a view 16, it sort of flattens the matrix, and it can be for a higher dimensional object. You can try to do in which along which axis you want to flatten it. Okay, so you can see the definition of view, like you give it a size, and then once you call the view function in along which like direction it will be flattened. So that's an useful stuff. So here you can see that if you sort of you had an X which was 4 cross 4, here when you do a x.view16, the output tensor has a shape like flat tensor, like a 1D object. The 2D object is seen like converted to a 1D object. Whereas if you do a x.view -1, 8, then -1 refers always to the last axis. So all the 16 elements are now arranged in a 2 cross 8 object. Okay, so like if the initial shape was say 24 and like let's say 4x6, and if you had done -1, 3, then you would have seen a 3, 8 stuff. So this is how view works. Like you say that in the last dimension what is the shape you want, and accordingly the numbers are rearranged. So this is a handy function. Like NumPy arrays also have this. So keep this in mind. Okay. Now, there are other numerical algebra handy stuff like transpose and things like that. So here you see that if you have some random, like a torch.random 1, 2, 3, 4. So it is a rank 4 tensor of in different direction it has different shapes. Now we can take any pair of axes and can swap the elements of the tensor. So here we have chosen to do it in 1 and 2. So it's like here 1 means the second column and 2 means the third column. So once we transpose it, the shape becomes 1, 3, 2, 4. So the 0th one and third one remain unchanged, and the second and third got swapped. So here, like this, if you have any arbitrary higher rank object, you can sort of permute, like you can permute or transpose the dimensions. Okay. And then you can also use the view function and try to check what things are doing. Now there is also like equality check in Pytorch. If you give two tensors of same shape, it will do an element-wise element checking that if the elements are equal to each other or not. And if it is the case that all the elements are equal to each other, then this torch.equal will return true, otherwise it will return false. So here in this case, B and C were sort of arbitrarily obtained. Okay. Uh, I mean, arbitrarily obtained in the sense that B was the transpose of A and C was just A dot view. So since the transpose was done, the elements are not same. So that's why it returned false. Now let's compare a little bit of transpose and permutation of a matrix. Okay. By the way, this class is until when? Like 11:30. Can someone confirm? Hello.
Usually it goes to 12:30. Uh,
Oh, it's 12:30. Okay, okay.
yeah.
Fine. Fine.
Uh,
We have ample time. Great. No, I was just thinking if I need to skip something. No, if it's 12:30, we have ample time. Good. So now let's see how transpose and permutation works. So let's say we have defined tensors, okay, of size 6. So here you can see that the A range function. A range means if you pass an integer n, it will just create a tensor, 1D tensor, where each individual elements are 0 to n minus 1. So this is how it is. And then we can, since there are 6 elements, we can sort of use the view function to rearrange the elements into a 2 by 3 matrix. So this is how it will get rearranged. Now, so it's a 2 by 3 matrix, and if we permute the two axes, then it becomes a 3 by 2 matrix. Okay. So in this case, transpose and permute do the same thing. Similarly, you saw that for a higher rank tensor, you can take the transpose function on any pair of dimension and can do the transpose operation. Similarly, you can do it on permutation. Now, since after all we are not here to just play with torch tensors, we have to do machine learning. There are some other things to remember. There are operations like torch.matmul, which essentially stands for matrix multiplication. So if a matrix is, let's say, of shape mn and another matrix is of shape np, then if you do matrix multiplication, then you will get a matrix of shape mp. Okay. Now, if you have two matrices of exactly equal shape, then you can do an element-wise element multiplication, which is of course completely different from matrix multiplication. Because if you have two matrices of same shape, if you do an element-wise element multiplication or operation, then the output matrix is the same shape of the input matrices. However, if you take two matrices and do a matrix multiplication, the shape changes. In Pytorch, there are like sort of smart functions to take care of that. One is matrix multiplication. So this can also be written as A, like this @ symbol B. So if you have two tensors, now the advantage where these things come in handy, if you have two tensors sitting on GPU, okay, and if you do this, if you use this notations A @ B, which is also valid in NumPy, or torch.mm or torch.batch matrix multiplication, which stands for BMM, then these operations are way faster than you write a routine to do matrix multiplication. So remember that. So whenever possible, try to use these functions. Now, the first non-trivial, like matrix multiplication, all of you are doing from school days. What is batch matrix multiplication? Remember that probably you have heard that when you do machine learning training, you need to do operations in mini batches. Okay, so I don't know if you have heard this phrase, but what you try to do, you take a chunk of data, which is called a mini batch, which has a finite size. You try to club few pieces of data and try to make operations on that. So let's say you have a mini batch where the batch size is B and the tensors are of, for the first batch are of shape NM and the second tensors of shape MP, then you want to do a matrix multiplication per batch element. Like if it's a batch size of 10, then you have first tens, like you have first list of 10 tensors and the second list of 10 tensors, and you want the first tensor from first list should multiply the first tensor from the second list. The third tensor from the first list should multiply the third tensor from the second list, so on and so forth. Now, if you're given two lists of 10 tensors, and if you try to write a for loop to do this one by one, that process is way slower than you're using this one-line notation of .bmm, batch matrix multiplication. Okay, so whenever there is a case where you can do operation on mini batches, try to use this .bmm. So make sure you understand that concept, that what does a batch matrix multiplication does. If anyone has any doubt, I can take a pause for a few seconds. Okay, so everyone is fine, great. Now, so let's take sort of a little hands-on examples of what all this does. So here again you see that we have like a matrix. We first created a flat matrix and then converted it into a shape of 2 by 3. Now, here you see that the view function also has been used. Now let's first do this. X is a tensor of shape 2 by 3 and W is a tensor of shape 3 by 3. So if you do a matrix multiplication, it will come out to be 2 by 3. So you can do it as a one-liner. Okay, X add W, and you can cross-check manually that if you are given two tensors, one with the elements 0 to 5, another with the elements 0 to 8, the output of the matrix multiplication is this tensor. Okay. Similarly, torch.matmul also gives you the same thing. So remember, it's the notation is like this is the first matrix, this is the second matrix, this is how it goes. So now, here you see that we want to deploy the idea of batch matrix multiplication. So we have created a torch like random number which is of shape 10, 3, 4. So this tensor we can think of as 10 individual matrices where each matrix has a shape 3, 4, and mat2 is like 10 individual matrices, each of shape 4, 5. Now, if we had written a for loop to multiply each of the matrices with each other, the for loop runs over all the 10 matrices, it would have been a slower process, whereas you can do it as a one-liner, just torch.bmm, mat1, mat2, and you can see that if you multiply 3 cross 4 matrix with 4 cross 5, it should be 3 cross 5 and the output matrix shape is 3 cross 5, but there is a 10 sitting before. It means there are 10 different matrices, pair of matrices which are multiplied with each other, and this is the output. Okay. Then there is also another handy stuff to sort of deal with the tensors and matrices. So now all of you like are more or less high energy physics enthusiasts. So you have dealt with tensors, and you know tensors have this like dummy indices. So if you want to do sort of matrix multiplication, you can use this thing called einsum, which is also there in the NumPy array. So you have, if you have two rank 3 objects, so you see that you want to, like the batch matrix multiplication, wherever there is a repeated index, that will be sort of summed over. Okay, so you have Pij and Pjk summed over j, that should give you an output index of Pik. And if you, this is how you define the contraction rule between two tensors and pass mat1 and mat2, it also does the job. So now you know multiple ways to make like contract, and you remember a matrix multiplication is essentially a contraction along one direction. So you know how to do it using several ways. Like you can do individual matmul, you can do batch matrix multiplication, and you can do like Einstein summation. So here, like, and this Pij, Pjk, etc., like you can give your own favorite set of strings. Just make sure that the dummy indices gets contracted in the right way. So I don't know if any one of you have used Einsum. I'm sure some of you have. Then this is also a very handy way. Okay, and if make sure that all the tensors are on the same device, otherwise it will throw a complaint. But once you do that, all these are equally good ways. Good. Any questions here?
Sir, for Einsum, how did you get that output? Like,
So Einsum, what it is doing, say matrix 1, it's a rank 3 object. So let's say, so rank 3 means it will have three particular, like 3 indices to denote an element. So let's say the Pijth element of matrix 1 and Ejkth element of matrix 2 are summed along, like the third column of matrix 1 contracts with the second column of matrix 2. So what will happen, that the first shape remains unchanged, because the first shape is P, here also the first shape is P, and here also is the first shape P. So it's guaranteed that if you give two rank 3 objects whose first dimension has size 10, the output should also have size 10. Now the rest is like Ij operates with Jk to give Ik. That means it's the third dimension of the first matrix contracts with second dimension of the second matrix. That's why the repeated indices will be summed over. Okay. So if you would have done, like matmul will always give matrix multiplication only, but if you wanted to do like some scalar operation, okay, that was also possible using Einsum. So in that sense, Einsum is much more flexible. So here Ij contracts with Jk to give you Ik. So and here that means 3, 4 contracts with 4, 5 to give you 3, 5. And that's how you get the output shape as 3, 5. And the first dimension is just remain untouched, P, P, and P. So if you go to the documentation of Einsum, it just explains you how it does. So you can see that if you were dealing with just matrices, not a list of matrices, you would have done matrix multiplication by Ij, Jk goes to Ik. Now if you want like tensor contraction of several types, say you have a rank 4 tensor and like let's take it this way, you have a rank 4 contravariant tensor and a rank 3 one form which is like covariant tensor, and you want to do sort of a contraction between these two to give output a rank 1 object. If you want to play this sort of games, then torch.einsum is more flexible stuff. Okay.
Okay, sir.
So
Thank
the
you.
summation is happening over only one indices.
Sorry, Shaurav, can you repeat?
So the summation is happening over just one indices.
Yes. So this J, the repeated sum index is J here. So the summation is happening over the repeated index.
P is also repeated.
Sorry, your voice is quite like.
So
Can you
P
repeat?
index is also repeating.
The P, yeah. So there is no contraction. Like the P carries forward. If there was a contraction, that index won't appear on the right. Okay. So let's say you have something like a tensor A mu nu sigma and a tensor B sigma rho alpha. So if you contract them, so the sigma is the repeated index which will be contracted. So on the output, there won't be any sigma. So here also you see the repeated index, the way we are writing that the fact that we are sort of omitting J index here, that means we are telling computer that do sum over that J index. If it's summed over, that means it doesn't appear on the output. The fact that the P is here, and also in the output, that means we are telling the computer that please don't sum over the P index. Is it clear?
Yes.
Okay. Great. Now, it comes to a very crucial concept, which is dynamic computation of the computational graph and backpropagation. So this is where, until now, there was no discussion anything specific to machine learning operations. Okay, but now we are sort of, given that we are familiar with the syntaxes of Pytorch, we are entering what are the core concepts of machine learning and how to deal with them using Pytorch. Great. So now, look, why these machine learning libraries are handy. They are handy for doing training on deep neural network because this machine learning libraries can automatically compute derivatives. Why derivatives? Because if in any machine learning operation, in any neural network, first of all, you should always think of neural network as a parameterized function. And the whole point of doing the gradient descent and the loss minimization is that we are sort of trying to adjust the parameters of this function so that they can represent that mapping between the nonlinear mapping between input data and output as universally as possible. Okay, when an analytic mapping is unknown. So when we do it through gradient descent and things like backpropagation, what we really need to do is to compute derivatives. So let's try to see what does it mean. Until now, we have defined torch tensors. Okay, so now x, let's say x is a torch tensor of any arbitrary shape. Then, if x is defined, when we are defining x, declaring it, if we define with the option that requires grad true, just like we can define it with a particular device so that the tensor lives on a particular device, we also declare it with the option requires grad true. Then if down the computation string, if we compute a function fx, then df dx, the derivative of this function with respect to x, is automatically stored or computed. And this is a great tool. Why it's a great tool? Because when you think of deep learning, like this architectures, the way it happens that output of one layer or one function goes to the second function. So this whole thing can be thought of a sequence of composite function where one function is nested inside another, so that whichever is like at the core of this nested function, the output of it goes to the second one, and the output of the second one goes to third one. And if you have to compute backpropagation, you have to compute the derivatives of all these functions. Whereas if you use this requires grad true option, then all the derivatives are automatically computed. So just let's try to see how it works. Let's say x equal to like torch.ones 3. Okay, which means x is actually 3 numbers. It's a vector. Now, if we print x dot requires grad, it says false, because we didn't declare it with the requires grad option, and by default, it's false. Now, if we sort of set the requires grad option to be true, it has been set to 2. Now, let's try to compute the following function. Let's say x is a vector of some arbitrary shape. So what we try to do, that with each element of the vector x, we try to add 2, take a whole square and add 3 to the number. And finally, divide it by the length of x. Okay, so the length of x in this case is 3, because it's a simple vector which consists of the elements 0, 1, 2. So if we add 2 to each of them, it becomes 2, 3, 4. Okay, and then if we square it, it becomes 4, 9, 16. We add 3 with it, so it becomes 7, 12, 19, and then divide it by 3. So let's do it. When we try to do it, you see what computer tries to do is the following. How computer looks into this operation, it's first with each element of x, it adds 2 and store it as a. Okay. Then when we are doing a whole square, it's defining a new variable b as a square. Now, with that squared object, it's adding a 3. Okay. And then dividing by the size and summing over means taking the mean. So it's c dot mean. Okay. This is how it happens. You see that when we do all these computations and print them, we get all these tensors, which we sort of did it through mental maths. But all of them has a grad function stored. That means all of their derivative with respect to x is stored. You can access them. Okay. So if you look into the picture, this is how it happens. This is called a computational graph. This is different from the graphs we will deal for graph neural network. So how a computational graph happens, that and the arrow of a computational graph, the edges run backwards. So first, what the computation we did for each x we added 2, okay, then squared, with the square we added 3, and we got the output. So when the requires grad true is stored, like it was declared, and you sort of try to compute the derivatives, at each stage, the derivative with respect to x is stored. Okay, so, but how do we access them? Look, initially, x was defined with a backward option requires grad true. So here, if you just find the x dot grad, like try to print it, it will return you none. So at this point, the derivatives are not stored at the computation stuff. Now, you do a y dot backward. So y dot backward, what it does, that it computes like, so y is a function of x finally, right? Through all of these options. Y is a function of x. So if you want to compute the derivative of y respect to x, you just call this function y dot backward. And whenever then you call x dot grad, the derivative del y del x is stored. Now how it works, when del y del x is stored, you remember that the intermediate step had all this computation. A is x plus 2, B is a square, C is b plus 3, so on and so forth. So del y del x, by applying chain rule, should be del y del c, then del c del b del ai, and del ai del x. Now let's try to see. What is A? A is x plus 2. So del A del x should be 1. Similarly, B is A squared. So del B del A should be 2A. Then del C del B again should be 1. Okay. So if you apply this, if you plug in these values, what will be del B, del Y, del C del BI, so on and so forth. You can compute that if you plug in x is 0, 1, 2, del y del x will be such numbers, because you can just compute del y del x on pen and paper. And then you go back here, it's 1.3 and so on and so forth. So it's 4/3 to 8/3. So whatever number we can compute by hand, those are automatically computed by the backward function itself. The gradients are stored. Now, for a very deep neural network, which has hundreds of layers with n number of complexities, you really cannot compute all the derivatives by hand. It's sort of impossible. However, if you use this x dot grad option and call the last function, where you call this backward function, okay, then it will sort of compute all the intermediate derivatives, and finally for the whole nested function, it will compute the gradient with respect to the elements of the input tensor. Okay, so this is the magic of like automatic differentiation or autodiff, which is part of any modern day machine learning tool, which is sort of utilized to compute the backpropagation. Like when the breakthroughs of CNNs and things like were happening in 1990s, these tools were not there, and very highly celebrated people like Ian LeCun and people sort of computed all this gradient by hand to sort of compute the amount of backpropagation and weight update which needs to be applied. So make sure how the like autograd is working and what is the basic concept, like at which step the derivatives are computed, and how using chain rule for a very deep neural network for a series of nested functions, the derivatives are computed. So any question in this front? Because this is a very important concept, that how exactly things are happening.
So if we want to calculate, let's say, del y by del b, then how will we access that? If we want to access that del y by del b only.
So you can you see that you did a y dot backward. Similarly, y dot backward means here it computed. But if you just sort of do a b dot backward and c dot backward, you can access all those numbers.
B dot backward would calculate for del B by del X. And if I want del Y by del V, then
So then you sort of detach the gradient from b once, and you have to recompute y as a function of b. And then if you call y dot backward, it will compute del y del b. Because here b was already a function of x. Okay. Now, so if you have computed b, you sort of remove the gradient, and let's say you create a new variable, let's say y1, which is just like like you first compute a c1, which is a function of b, and then y as c dot min. And then if you do y1 dot backward with this new variable, it will compute del y del b.
okay, sir. Thank you.
Yeah. Any further questions? Okay. Great. Now we will sort of try to do a little back propagation by hand. We are still not using any machine learning tool or so forth. So what we are trying to do, we will have something like an input tensor x. We will have matrices W1 and W2. So what we are trying to do, we are trying to emulate a very simple, like two-layered stuff. So there is a weight and an activation function and another weight. Okay. So this picture we want to code up by hand without using any explicit machine learning tool to build our intuitions. So let's do it. Let's say we have an x which is of a shape like n, and the shape is d in, which is like defined here, and d out, all these integers are defined here. Now let's say we want w1 and w2 are the sort of parameters which we want to update. So initially we define w1 and w2 as random numbers. Now what we are trying to do, look, here for n number of epochs, we are first trying to do a matrix multiplication. X dot mm w1 means w1 from left acting on x. We get something. Now we sort of introduce an activation function. We will come to more details of activation functions. But remember, activation functions act as filter and they don't have any trainable weight parameters. So what we do, we use this notation h dot clamp mean equals to 0, which means in this tensor h, whichever values are below 0, you set them equals to 0. And that is what rectified linear unit is, like just whatever is the negative stuff, set it to 0. So we get something like h value. So here, if you follow the formulation, so first when we are doing like x dot mmw1, we are doing this stuff. Then when we are doing a clamp to 0, we are essentially like operating this activation function. And on the second step, we are again multiplying by W2. So once we do these 3 consecutive steps, we are actually doing this functional operation by hand. And then we sort of do a mean squared loss, which is, you know, that it's the Euclidean distance between two tensors. Now, here you see that since loss is the output with respect to which we are taking the derivatives, we sort of do a back propagation by hand. So first of all, if you have a y minus y prediction whole square, its derivative is 2 times y prediction minus y. Okay. Now, we first need to compute the gradient with respect to the W2. So that's when we are trying to do. It's the output del L del W2, and that should come as H relu times H relu. Remember, it was the output of the sigma. So we do a matrix multiplication, and then the grad H relu is the gradient with respect to the previous layer. So what we all did is that whatever will be the task of automatic differentiation, here we are doing it by hand, just to show you that even for a simple layer where there are two weight parameters, if you have to compute all the derivatives, you have to just code it a lot. And you do finally like weight parameter update. There is a learning rate, which decides how much you actually move in the parameter space when you're trying to do a back propagation, how much the state of the neural network architecture changes. And this is how actually back propagation works. So you have a loss function, take the derivative with respect to the weight parameters, and then update your weights based on the computed gradients. So this is like the core zeroth concept of a neural network training, which has been deployed by hand, just to show you how each and every component works. Okay. Now, sort of you can see that when we try to do it, the loss function sort of decreases rapidly, and this shows that this is the basic intuition that if you define a loss, the loss will go down when you do a neural network training. So this is like absolutely a toy network for which we have a simple perceptron where you have a linear layer, activation function, again linear layer. So this perceptron, how it works. And now once this is done, let's sort of embark into how you do it professionally. But from a conceptual point of view, are there any sort of blockage? That how under the hood, how the simplest of things work? No, everything is good? Okay. So now we will try to do the same thing. But the neural network layer, which we sort of coded up by hand, we will learn how to do it using an nn.module in Pytorch. Okay. Sorry, here it's a spelling mistake, so let's fix it. Great. So what we will do, we are doing the same thing. We are defining the input tensors and the target. Now you see that the matrices which we defined as W1 and W2, here we sort of are declaring as linear layer. So linear layer is just the matrix multiplication, and everything is now coming from this library which is called torch.nn. So if you want to draw a one-to-one correspondence, whatever was defined here is as W1 as torch.ran number. The same thing here is done through torch.nn linear. So we had two pieces of W's, which is two linear, and the ReLU was implemented by clamping the output tensor. Whatever was negative will be 0. So here from the same torch.nl library, we are calling the function ReLU. And if you have any doubts anywhere, just go and place your cursor and it will give you the description. Now, it is very important that you put all your input target tensors and the weight parameters on the same hardware device, otherwise it won't work. So here see, the model is analogous to the function, neural network function. We put it on the device, and whatever is the mean sum square error loss, we also have that built inside Pytorch. So now, once we have that, we sort of try to redo the same exercise which we were trying to do earlier using Pytorch. So what we are trying to do, look, we have an X, which is the input data. Whenever you call this notation, model X, it means model was a sequence of 3 functions. So this input tensor X goes through the sequence of 3 functions, and the sequence is the way they are defined. So first, when X is given as input, first it goes through this linear layer, then goes through the activation function, and then goes to the second linear layer. And what you get Y prediction is the output. Now you have a target function Y, and you have a well-defined loss function. The loss function was defined as MAC loss. Now the reduction is given as sum. You can change the reduction to mean as well. So the sum is like just sum over, say, delta Y whole square, and mean will just divide the whole thing by the shape of the tensor Y. Okay. Now, once you sort of compute the loss, you can print it. So it says every 50 epochs, just print the loss.item. Now, here is the very important concept or the step. If you define a model, you really don't want to have any memory of pre-computed gradients with respect to its weight parameters. So first you just clear all possible stored gradients. So you first do a model.0grad. Okay. Now, when you call loss.backward, then every trainable weight parameter which is appearing in the model, the neural network, the derivative of the loss function with respect to those weight parameters are computed. And that computation happens when you call this loss.backward. So you think how powerful it is, that it can be like a 100 layers deep network. So if you really have to compute like the derivatives, you have to compute 100 different partial derivatives, and like that's in the knife way. If you have to compute with respect to each tensors, like each layer can have many different weight parameters. So maybe sort of million partial derivatives you have to compute by hand. But here, whenever you call this loss.backward, all of it is done at one go. So this is the power of this automatic differentiation. Now, here it's still, we have computed the derivative, but we will do the weight modification by hand. So what we are doing, so first of all, look at this syntax, param in model.parameters. So model.parameters return you all possible weight parameters. And each weight is sort of done like subtracted by a learning rate times param.grad. What is param.grad? If a parameter is w, then param.grad gives you the number del L del w, the partial derivative of the loss function with respect to that particular parameter. Okay, so now if you run it, the sort of the weights will be updated. So again, here we see an example where the weight modification happens and it decreases. Good. Now, in the previous example, the computation of the gradient was automatized, but the backpropagation was done manually. Now we will also make the backpropagation automatized. So how do we do that? We will use the optimizer. So again, the same sort of example. Exactly, we are trying to repeat the same exercise, but each time we are trying to replace one operation which was done manually by an automatized way. So first, it was defining the model architecture. We have defined that. Then we did the backpropagation by hand. And now the weight update, that will be done through an optimizer. So up to model.device is sort of trivial. And once you have done a model.toDevice, look how we are trying to do. You do the forward computation. Now you call the loss.backward, which means it sort of computes the gradients. Now here, there is something called optimizer. Okay, so optimizer was defined as stochastic gradient descent. It was already sort of defined in the previous, it's the MSc loss. Let's try to see. Yeah, here the optimizer was defined as Adam. Now, whenever you called optimizer.step, now, first of all, what does optimizer takes? I mean, there was a comment that the loss is going down whenever you automate the code. If you do it by hand, it will also go down. So look, what optimizer takes. Optimizer takes all the weight parameters of the model, and there is a learning rate which is given to the optimizer. So first of all, when you do optimizer.0grad, the optimizer is free from any pre-stored derivatives. Now when you do loss.backward, whichever weight parameters were given to the optimizers will store the derivative of the loss function with respect to all those weight parameters. And when you call this optimizer.step, exactly the operation which you see here is done through that single line, that the weight modification, the weight upgradation is done through this optimizer.step. Okay, so all of the modules of a training which were done earlier manually, there are ways to do them through some one-liner syntaxes. Yeah, Bapi Boshak is saying that the automated ones has less loss because you have already trained the model before. So it's sort of showing you less loss, but it can happen because also when you redefine a model, it's sort of created with arbitrary weight. So it depends on the loss landscape where the state of the model is placed when it's defined for the first time. So depending on that, if you do number of training for fixed number of iterations, it can have lesser loss. No problem with that. Okay. Are there any further chats? Let me just check. No, it's fine. So good. Now, we have to learn how to then construct the neural networks in Pytorch syntax, because neural network are functions, right? A function for which you need to have a rule for the forward computation, and it also should have the weight parameters, right? So let's try to do this. So any neural network architecture or model in Pytorch is inherited from nn.model. Now, at this point, how many of you don't know class inheritance? You can like raise your voice. I will try to put it in. So Neeraj Kumar says, Neeraj, you don't know class inheritance. So that's not a problem. So class inheritance means you have a predefined class. When there is a class, there are like member objects and functions. Some of the member objects and functions are private, some are public, but they're there. Like all those member functions, they have properties, and you try to encode the properties when you write a class. Then you want a new class which will have same properties as before, but on top of that you want to add new variables, new functions, so on and so forth. So in that case, what you do, you inherit from, like, it's like a family business. Your like previous generation created some wealth. Now you want to inherit it and then do business on top of this accumulated wealth. So class inheritance follows that concept, that whatever hard work you did to define a class, you sort of build on top of that. You inherit that and then define a new class where you add new functions and things like that. So that's what we are trying to do. So you see, when we are trying to write a class called my module, we are inheriting it from something called nn.module, which is like a class already written. Now, here, like the constructor goes under this init with a double under or dunder. So whenever you will define the layers of this module, it will go here. We will go through a sort of example. And the forward computation rule also have to be defined. So since we haven't defined a proper module here, so we just keep it as a pass. What this syntax means, that my module will have a member function which has a forward function which will do the forward computation. Okay, so we will use this syntax to write down a simple perceptron. What it will do, it will take the input data, will pass through some weight parameters, apply some activation function which is filtered, and will give the output. Just that simple stuff. So how we will write it? So again, a two-layer stuff. You see, we have inherited a class, like we are inheriting a class from nn.module and defining our own member class called simple classifier. So in the sort of init stuff, if you can define the layers in this way, and it's the Python syntax. When you define an object or a function with self, it becomes the member functions, right? So self.linear, self.activation, blah, blah, which is, the first one is linear layer, then a tan hyperbolic activation function, another linear layer. And here you define the forward computation rule. So if you are given an input vector x, first it will cross through the first layer, then the output of the first layer you store in the variable x. So at this stage, the x here and this x here is different. The updated x goes to the activation function. So the output of the first layer goes to the second step, and it is passing through some activation function, which is tan hyperbolic. It's applying like -1 to +1 bound, but there are no weight parameters. And once this modified distribution, it's passed through again a second layer, which has weight parameters, and finally you're returning that. So you have two layers here with one activation layer sandwiched in between them, and you're giving an output. So this is like the simplest example how you code up a perceptron with two linear layer and one activation layer. And remember, if you had two linear layer, one following other, then it's a linear layer itself. So you can't bring non-linearity. So the activation functions are pretty crucial to bring non-linearity into the system. Okay. So let's you have defined a model. How we can use it? Let's try to use it. So let's write down the model as a simple classifier where you expect that the the feature dimension of the input vector of size 2, then num hidden, which was used to create sort of embedding dimension. So the feature dimension 2 gets mapped to an embedding dimension 4, and then that 4 reduces to 1. So sort of बाद में, अब बाद में. So this is how it works, and there is an activation function. You can print it. So now there is also a new syntax. If you print the model.children, then it gives you access to all the individual sublayers inside like a complex layer, and you can access their weight parameters as well. So if you see that if you want to sort of access the trainable weight parameters for each individual layer, you can use this syntax. Like in the model.named parameters, it will print the layer name, and it will sort of print the individual numbers, right? So first of all, before we sort of go to the next step, is it completely clear that how you will write a simplest model in Pytorch and what the syntaxes you will follow, and where you will declare the trainable weight parameter, and how will you compute the forward computation? These few steps needs to be absolutely clear.
So what are those 4 hidden,
So
like,
So when you see the picture of a neural network, there is an input layer and an output layer. And then there are intermediate hidden layers, right? So how do you code that up? So you will code up like, here there is only one input layer and output layer, and there is an activation function. But you could have declared here linear 1, 2, 3, blah, 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 whatever name you like to give. But then the forward computation rule, how the input data will be processed, that rule you actually hand code here. The rule you specify through this snippet, which is of course an example, that the input vector goes to linear 1, which is first layer. Then the output of the first layer goes to the activation function, and again the output is modified, and at the last, the output of the activation function goes to layer 2. So this is how this series of nested function works. And finally, after going through few stages, the output, like the variable which you have, you sort of return it as the output. Okay, so you could have introduced many more layers here, and depending on the way you write down the forward computation rule, some layer will, like there will always be 2 layers, which is one input layer, output layer, but the intermediate ones will be sort of called hidden layers. Okay, wait for a minute, I will like put charger to my... Any further questions?
Sir,
Yes.
sir, if we want a larger number of hidden layers, how would we automate this process in that case?
We will go through that. Like you can sort of give a list, and then there is an automatized way in the for loop where you can define how many number of hidden layers will be there and what will be their shape, so on and so forth. Okay, and then we will introduce something called nn.module list or nn.sequential to club all of them together. We will go through this example. Great.
Sir,
Yeah.
sir, in the previous, in which you automated that weights were getting updated, that part I didn't get. Can you please explain that? That weights were getting updated.
So weight, So first of all, when we were doing it by hand, you saw how the weights are updated. Like each weight, W, goes to a new number, which is, let's say, W prime, which is W minus the learning rate, epsilon, times the rate of the derivative of the loss function with respect to W. So W prime is W minus epsilon times del L del W. Whenever you call this number param.grad, it returns you that del L del W. So whatever the weight upgradation rule we were trying to code by hand, here through optimizer, you can all do it in one step. So whenever you do loss dot backward, all the del L del W's are computed, and then you do optimizer dot step, then you have the function. Like this is where the W minus epsilon dot del L W computation is happening.
Okay, sir. Got it. Thank you.
Great. Now you have learned how to sort of define a function. We really need to learn how to sort of customize, write a custom data load, customize the data. Okay, so there is a class called data which is defined inside torch.utils.data. What is like a dataset class should have? Look, like there can be like ready-made data like images and stuff like that, but all of you who are working in some branch of natural science may get like raw data from your setup, from your scientific setup. Now, how do you sort of wrap up inside a little box so that your data set is custom ready for machine learning purposes? That's something you have to learn. Like you may be working in a laboratory, you may work with some simulation, some theory computation, but you really need to learn that the numbers which you're getting, how do you readily make, like how do you groom it so that you can use them for machine learning purpose. And that's what we will learn through this sort of code snippet. So look, let's say there is some random number which is generated, which has some labels. So we will try to see what numbers are generated. But for the time being, see few parts. So every data set in Pytorch will again be inherited from Torch dataset, so XOR dataset. Then there should be this function len, which should tell you like how many numbers of data points you have now, and the get item, which are all like functions which are predefined in this data set. It gives you access to a particular element. Okay, so now let's see how things goes. So first of all, let's try to visualize the data set which we are trying to generate. We are trying to generate a set of scattered points in a 2D plane where we know the coordinates. So depending on the coordinates, you can think of this as like first quadrant, second quadrant, third quadrant, and fourth quadrant. So if the data, the points lie in first or third coordinates, we just label them as 0 or say class 0. Whereas if the data points are lying in the second and fourth quadrant, we call it class 1, the alternative class. Okay, so depending on their location, we sort of want to generate a data set which can be of either of the category. This is just a toy data set, but this will help us to formulate a classification problem. You can already see that this data set is like labeled in two classes. It has two colors. So we sort of can use it for a toy classification data set. Now, how do we generate it? You see, like we are generating random number between 0 to 2, okay, and then sort of sum it over. So each data point has a coordinate. So we are generating the coordinate, and how we are sort of generating the label, that along the second dimension, if the sum is 1, then we are checking if it's equal to 1. If it is 1, it comes to be, the label comes to be 1, otherwise 0. So the label are 0 or 1. And the get item just returns one of the point and the corresponding label, and it returns it. So if now here through this syntax, sort of we can choose how many data set we want to generate. It will generate 200 such points, random points, but based on the location in the 2D plane, each point will have a label. So we sort of can print that each individual point, and each individual point comes with a location in the 2D plane and the corresponding label. So this is just a toy data set, okay? But we can do some classification task with this toy data set. So similarly, like data set, you can, like among 200 data set, you can pass an integer and ask what that data point is. So it will tell you the data point lies here in my 2D plane, and given there is a location, this is the label. So that's the visualization. Now, for machine learning, we already told you that there is a concept of mini batch, so that you do machine learning operation not on individual data points, but on a chunk of data points. And that has to be done through this data loader class. So what does data loader class takes as arguments? It takes the batch size. First of all, if your, like, each individual data point should be independently identically distributed. Okay, so so how it goes, that you specify a batch size, you tell whether to shuffle it or not. If they're truly independent, then the shuffling shouldn't matter. Okay, and then you sort of use some pin memory for GPU issues, so that can come later. So what you do is that you have a whole data set, let's say 1,000 points or whatever individual number of data sets. You pass it through a data loader and specify a batch size. The batch size, what it will do, it will split the whole data set in batches, where each batch will have the given number of data sizes. Okay, and the shuffle will ensure that given a batch, the elements are given some random permutation. That's how it works. Now, if you want to see how, so if you have 1,000 data size of data set, and if you make the batch size 10, you will have 100 batches, and you want to see how individual batch element goes. Like here it's 8. So you see, we have 8 points. So 8 points have 8 coordinates and 8 labels. Similarly, depending on your, so as if you had individual data points and you have stacked the number of batch size amount of data points together. Okay, and that's it. Now we have the model, we have the data. Now we have to define a training. Now how do we define so we want to do a classification task. Like first we want to train the neural network model by showing it, look, here is the location and here is the label you will learn. So once you, and we don't tell you how you compute it, we will just show you numbers. And once you are trained with enough number of data points, now we will give you arbitrary points and you have to tell me the label. Okay, this is the way we will do. So for that, since we are doing a 2-class classification, we sort of choose a cross entropy loss. It's a binary cross entropy loss. Okay, so that's the loss. And we have chosen something called stochastic gradient descent optimizer. So later, like if time permits, we can talk about what are the different optimizers, so on and so forth. But for the time being, you could have chosen Adam. You can do experiment on your notebook by choosing whatever you want. You can choose a learning rate as well. So just remember that all the weight parameters of the models are passed to the optimizer. Now let's see how we set up the training. So we have a training data set with 2,500 points. So once we have a training data set, we have a data loader, and you can see we have sort of given a large batch size, which means 128 points together will be clubbed into one batch. Now you put the model on the device you are working. Now let's try to see how you're sort of set up the training. So you're calling this. So you specify the number of epochs for how many iterations you will do the training. And then for data inputs and data labels in data loader, this will ensure that there is an iteration over all the mini batches. So you take one chunk of batch one at a time and load that batch on the device, which means if you're doing it on a GPU, this is the step at which you will put it on a GPU. Now you have an input data, pass it through the model, so you will get some output predictions. Okay, so you have a mini batch of predictions and you have a mini batch of targets, so you can compute the loss. So here, when you compute the loss using this function, you compute the loss for whole mini batch, and then you sort of do an optimizer.zeroGrad so that all previously stored gradients are cleared off. You do a loss.backward and do an optimizer.step. So it's on the, now you're computing the loss from the whole mini batch and doing backpropagation based on this computed loss, and you can print it. So you can see that when we start printing it, the loss starts from 0.71 and sort of keeps decreasing. We did it for quite some epochs, so it sort of decreased, which means this simple network sort of learned the data. How fast or how slow it's learning, that's a different question, but the fact that the loss is monotonically decreasing, it means it's learned the data. Okay, so once you have saved the model, you can save it to something like the state dict, which is the model state dictionary. You can save it to an output file, and you can just print that, just show me what are the updated weight parameters through this print state dictionary. Now, more often what you will do, you will save the best trained model, which may not be the last epoch. I mean, there can be overtraining. So you will sort of pick up the best trained model and try to use it for all further purposes. So you have a best trained model, which we name as our model.pt, and then later load it for future usages. Okay, so if you specify the architecture and you use this syntax load state dict from pre-trained weights, then the newly declared model sort of copies the weights and just becomes like a trained model. So you can sort of cross-check that the model which you stored versus the model which you loaded have the same weight parameters. So you just print the original model and newly loaded model, and you can see all the weight parameters same. Now, how do you evaluate the performance? Okay. To evaluate the performance, of course, you want to evaluate on a data set which is completely new and which was never used during the training. Okay, so that's what we call as a test data set. So again, you create a test data set of size 500 and you have a test data loader. Now you want to sort of compute true positive versus false positive and things like that, which means which are the cases for which the true label was 0, but the model predicts also 0 versus true label as 0 and the model predicts as level 1, things like that. So you sort of define an accuracy score based on the true positive and false negatives. Okay. So the accuracy score is defined, and now you can sort of compute the true positives. So the output is sort of, once you get the output, you can associate a label 0 and 1 based on the score. So if the prediction is between 0 to 1, whichever has predicted score more than 0.5, you can label it as 1, and whichever has predicted score less than 0.5, you can label it as 0. So then you just count what is the predicted labels is equal to the truth label. Okay, you can count the number of true predictions and compute the accuracy. So here I sort of train multiple times in my notebook, it coming 100%. Also the data set is trivial, but for all realistic data set, you won't reach 100%. Okay, it will always be less. Okay, here I had some problem. So let's say we have the test data set. Here is the test data set, which has class 0 points here, class 1 points in the off diagonal. So this direction. So now we want to see that given these points, which are shown to the the trained model for evaluation, the given color is the truth labels. Now, what a trained model predicts? Let's try to see. So, how do we do that? So, we sort of write a matplotlib code snippet to figure out what the predictions are, and we predict it. So those of you who have played with some Python, which I'm sure all of you have, this is just a fancy way of plotting. Okay, so here you see that sort of the neural network says whatever is along this diagonal patch, the orangish patch, it identifies as class 1. Whereas whichever one is on the top right and bottom left triangular wedges, it identifies as region for 0 points. So, I mean, it always say, now it's saying that it identifies or inferred that the classification happens along these zones. It's split up in 3 zones. The central continuous zone, it identifies as class 1. Whereas the 2 off diagonal triangular wedges, it identifies as class 0. Okay. So, and okay, here sort of I didn't show the TensorBoard logging, but you can do is that if you want to monitor your training, etc., in real time, there's a thing called TensorBoard, or in Pytorch Lightning also you have this. You sort of can use it. The code snippet is given, but that's for visualization or sharing stuffs with your collaborator. But what I wanted to show you some basic example, that starting from very basic notations of torch tensors, how to sort of build a model, a data set, and where the stochastic gradient descent and weight updates sort of creeps in, and how do you do a simple classification task. Okay, so this is sort of one full exercise. So please, I'm sure you have some questions at this point. Please ask.
Yeah, regarding the batch size,
Yes.
how would it affect actually the grain model?
So first of all, if you have very large batch size, then the fluctuations, the statistical fluctuations from one point to other is much less, because the loss you are computing is by accumulating the data points from all the elements of a mini batch. But on the other side, the drawback is you have to load this full mini batch on your GPU. So your memory will be jammed. So it's always like a compromisation between the numerical floating error versus your computer memory. So depending on how heavy your individual data points are in terms of computer memory, you choose a batch size.
Okay.
Yeah. More questions? I mean, if there are no questions, I will just show you some intuitive stuff about activation functions and how they work, their comparisons. But before going there, I wanted to sort of confirm that you really understand how each step of a neural network training works. Like, how do you construct the basic model, the data set, the data loader, the training loop, so on and so forth. Because in the main school, this will be sort of assumed that you know everything of this.
Also regarding the batch thing, another question I have.
Yeah.
I think you mentioned something about the data points being independent in this case.
Yes.
Uh, but uh, if that is not always the case,
No. Then there is something problematic with your training data itself. Like, first of all, the, let's understand this. Why you're doing machine learning? Like, it's an under the cover assumption that all of your data points are sort of drawn from some higher dimensional probability distribution function, and you don't know that probability distribution function. So when you say I want to do machine learning or learn pattern on the data, what you intrinsically trying to do, you're asking a nonlinear network, where these nonlinear networks are universal approximators of a nonlinear function, to learn that higher dimensional probability distribution function from which these data sets are sampled. So a finite training data means each of the data points are independently and identically drawn from a distribution. These are IID data points. Okay, so if that's not the case, then this whole sort of chain of things can break down, because it depends on the assumption that the data points are distributed independently and identically. So if you just plot the training data, the profile should give you what are the nature of the underlying probability distribution functions.
And that is true even if we are trying to learn, let's say, a posterior.
So if you have a specific like particular issue in mind, you can just tell right now that what kind of data you're looking into so that I can address the issue.
No, I was just wondering if that has always to be the case, that the data points are independent, but you're saying that it has to be so.
Yeah.
So, okay, that was what I was looking for.
Mhm.
Okay.
Okay, so we are sort of. I was told I can go until 12:30, right?
Yeah, Sanjita, you can go till 12:30.
Okay, great. So let's now sort of try to do some little bit about activation functions, because like it's always, I mean, there are many different issues. So I thought a quiz. Okay, I will just try to sort of settle that down with Riteshta, and you will get some quiz. Don't worry. Like either like in the second half today or tomorrow. Let's see. But let's first go through it. So for the, Riteshta, are you online? I see you logged in, but probably not. Okay, fine. So, look, this piece of code, the second code about activation function, it sort of downloads some data called fashion images, which are like images of some fancy boots and dress and things like that. Now, we want to know some properties of the activation function so that you can build your own intuition of which activation functions to choose. So, how activation functions actually work? Like, sort of any function which has a forward computation. So you've also seen that activation functions are just like layers, right? It just don't have a trainable weight parameters. So you can always think of activation functions as something which is sort of inherited from an n-dot module. And then you write the forward computation rule. See, the sigmoid is sort of 1 by 1 plus e to the power minus x. Okay, 0 to 1. Then the tan hyperbolic ones are, you know that how to compute tan hyperbolic functions. There are rectified linear unit, which is essentially whatever x greater than 0, it will be retained, and whatever x less than 0, it will be sort of set to 0. And then there is a leaky ReLU where you can specify a slope, and all the negative things will be sort of multiplied with that slope. Okay, so on and so forth. There is something called ELU and swish. Swish is just x times sigmoid x. So let's try to, like, these are sort of common activation functions. So let's try to build an intuition. Why we need to build an intuition on top of that? Because remember, when we try to compute for the back propagation, when we try to compute the derivative of the loss, if you apply the chain rule, all the derivatives of the loss, like these activation functions, have to be pre-computed. So since they don't have any weight parameters, we just want to build an intuition that how the each activation functions and their derivatives looks like, and how things can be sort of adjusted and how they're used. So how we sort of compute the derivative you see, we are like, if there is an x, which is an input vector or tensor given, we are cloning it and then setting it to be requires grad true. And then when we pass it to the activation function and call the backward, whenever we sort of return x dot grad, since x is passing through the activation function, x dot grad will return the derivative of the activation function with respect to x. Okay, so this is a nice little code snippet which is used for computing the derivative of the activation functions. So now there is like a little code snippet to just plot it. So if we are given x, we can first compute y. So y grads are like, y is the output of the activation function, y grads are the derivative of the activation function, and you would sort of generate x as some n number of random numbers sort of thing, and then plot the function y, which is the activation function itself, and the derivative of the activation functions. So you can make this plot. So here you see how things are working. So the sigmoid, which is like within 0 to 1, that the gradient sort of grows up close to 0, and then again goes to 0. Tan hyperbolic again has this goes to 0. ReLU sort of, here is the activation function, and the gradients are just step functions, both for ReLU and leaky ReLU. And for swish, which is x times sigmoid, it's the gradient goes from 0 to 1. Okay, so like, first of all, you see that the gradients can vanish. For many of the cases, like y over sigmoid or tan hyperbolic, ReLU or leaky ReLU became sort of popular, is the following, that this sigmoid and tan hyperbolic suffered from a problem which is called vanishing gradient problem. Their gradients also vanish for certain values of x. Whereas like for ReLU and leaky ReLU, you know in the negative side is vanishing. So for whichever negative, you have trace of the derivative. But also if it's positive, the derivative is 1, which is a good number. It's not a variable, it's 1. And it's a finite value. So when you compute loss, the loss doesn't vanish. So this became pretty popular. Okay. Now we can sort of, now we have built the intuition of how different activation functions and their derivatives are working. We can sort of set up a little training and see the effect of different activation functions. So we have sort of written a base network and downloaded the ImageNet dataset. So you can look into this in your free time, like this from the Torch Vision datasets. You can download fashion MNIST. So just in the grayscale image. So these are object, maybe you can think it's like spooky stuff. It's worn by ghosts, but these are like low resolution images in black and white colors. Okay. And we sort of do some training. Okay, so once we do a training, which you can see the net.0 grad, the loss dot backward, etc., which are part of the neural network training, we wanted to see how the weights in the network and how the outputs of the activation functions change it. So you see, so there in this neural network there were a few layers, and this is how the weight parameters varied when you use sigmoid activation function. So there were bumps which will make your training goes sort of nuts. Whereas when you use tan hyperbolic, they are sort of much smoother. Same for ReLU and leaky ReLU. And precisely what I said, the sigmoid, since it suffers from this vanishing gradient problem, this sort of zeros start appearing in the weight because there's no weight upgradation and it's a multiplication by zero. So you can see that the advantage of tan hyperbolic and ReLU over, say, sigmoid in this case is demonstrated that how the trained weight parameters sort of behaves. They are sort of much more smooth functions and centered around zero, so sort of Gaussian and stuff like that. Okay, so it's similar things for leaky ReLU, LU, and all this stuff. So this also tells you that you can directly verify the effect of choosing an activation function, not just from the end result what you want, but from the distribution of the weight parameters you have obtained. So that's an interesting insight. And in this notebook, what we did, we sort of did some again, image classification task, which probably you have heard by now, and test that for the same data set and the same network architecture, if we just replace the activation functions, are there any impact of the activation functions? So we wanted to see how the outputs of the different activation function goes like. So we had a linear layer and the output is sigmoid, it's behaving well. But when you are going for a deeper layer, the output of the activation functions have these lots of kinks. So I encourage you to run this notebook and try to play with that how the weight parameters and the output activation functions plays a role. Okay, but for tan hyperbolic, you see the distributions are much smoother. So this is like a direct demonstration that after the training is done, what is the impact of activation functions. So similarly for ReLU, you can see it's centered around zero because the rest is cuddled off. However, the distributions are sort of smoother. Same for leaky ReLU and LU and swish. So this is also a way that once you sort of have done a training, just try to visualize how things are going. Okay. And then finally, I wanted to talk about some dead neurons whose some weight parameters for which del L, del W becomes zero. Those are called dead neurons. And in that case, the backpropagation won't update the weights. So there are ways to find out the gradient and identify the dead neurons. So probably you may want to omit them from your evaluation. You can just count that given, let's say, a model parameter has 1,000 trainable parameters, how many are dead parameters, which means their gradients are zero. So this is another hand. It's a good thing to know that how activation functions are sort of playing a role in a training, since you will use them anyway. So I just didn't want to go through line by line for this notebook because the codes are there with you, and given that we have went through the first notebook in all details, you can now read it, but I just wanted to give you the intuitions that how things are working under the hood. So now you can try to run it yourself, and the codes are up there, you can play with it. Okay, so that's all I wanted to discuss. So are there any questions?
ReLU, the gradient of ReLU is not continuous at zero, right? So how is it handled?
So, I mean, the gradient is not continuous at zero, but you have a value for the gradient. If the input value of the tensor is negative, the gradient is zero, and this is what causes these dead neurons. However, if the input value is greater than zero, then the gradient is +1. So the fact that this is discontinuous doesn't affect you. You just know what number to pick.
Oh,
Uh,
okay.
to train a model, which activation function will be using and how many layers? How do we decide that?
So that's a part of hyperparameter optimization, and that you have to learn. Like, there is no fixed prescription. You have to play with this and learn, like how deep you want to make the network, which activation functions you will use, etc. What through this second tutorial, what I wanted to give you is that if you use different model architectures and activation functions, how will you sort of trace back the impact? That's the thing.
Okay.
So the graph that you showed for distribution of weight parameters, how does it help us in deciding which activation function that we have to use?
No, I mean, once you train something, you will realize that when these activation functions and their derivatives, like the output distributions are smoother, the convergence of training is much more well behaved. Whereas if the output is such shaky ones with spikes, the convergence of the training is bumpy. So once you do a training yourself, you will see this.
So is there any proof for this particular observation?
Yeah, there are mathematical proofs to it, like how active, like the theory of activation functions, like all this whole machine learning stuff is based on very rigorous mathematical stuff. So here we are just giving you some certain hints and ideas how to build, how to deal it in an intuitive way and to get things working. Okay, further questions?
If you could please share some references for the theory part of this.
So what I will do, I will like mail you. Okay.
Yeah.
So I'm sort of done with what I plan to cover here, and maybe I will create a small quiz. Like, I mean, you just really don't uh, get much out of the quiz just to filter some people, but uh, you actually learn the things when you sort of practice and try to read everything yourself. So I will create a small quiz and I will give it to Riteshta, and let's see.
Yeah, we can have that in the second session. That's okay. So, okay, if you are done here, then we'll stop for today. Sorry, for this session, and we'll meet on, I hope, 2:30.
So okay, so I will then stop sharing. Okay.
Yeah.
Okay. Thank you.
Okay, thank you. Okay, bye-bye.
Okay. Bye. So I'm logging off. Okay. Bye.